Problem is the old Three Stooges question. Get rid of this star. All right, so a survey of faculty, grad students at the University of Florida's film school revealed the following: that 51 of them admired Mo, 49 admire Larry, and 60 admire Curly, 34 admire both Mo and Larry, 32 admire both Larry and Curly, and so on. You could read. I promise that we will get to problems more interesting. And in fact, an activity that I have in store for you next week is going to involve data collection, where you decide on the topic of interest instead of me deciding on it, and then you can collect and determine some probabilities for that. All right, so more on that later, but for now, let's enjoy the Three Stooges. So we need to make a Venn diagram, and then from there, answer some follow-up questions. This is a how many. This is how many people were surveyed, how many admire Curly, but and so on. That's the beginnings of probability, because that's giving us the top number. You know, probability is going to be a fraction. It's going to be a ratio. Right? Part out of whole. So in effect, we're learning how to determine the parts and the whole so that we can piece it together down the line and make some probabilities out of it. And in fact, I could even show you with this example. But the first thing they want us to do is talk about the three individuals here. So that's going to be three circles in our Venn diagram. So I like to make it nice and big. Let me get rid of the shading because I don't need that. Actually, while I'm at it, let me turn the shading off because it's going to be something I'll have to delete every single time anyway. So, three circles overlapping. It doesn't have to be a thing of beauty. If it can be, sure, let it be. But it's just, you need to have a rectangle containing three overlapping circles. All right. So we have three categories. We've got the Mo category, M for Mo. Do a quick underline of the M. That's terrible. M. Larry, L for Larry. If the abbreviation is obvious, you don't need to create let statements or anything like that. You just make it obvious what these letters represent. And in this case, I think it naturally is obvious. M, L, C, Mo, Larry, Curly. All right. So, in fact, I'll use a highlighter here, make it look a little bit nicer. All right. So, the M for Mo, then we'll have Larry, and then we'll have Curly. All right. So, 51 admire Mo. What that means is that the entire circle for M contains 51 individuals. All right. So, 51. This is a survey of faculty and grad students at the University of Florida. So there are 51 people who said Mo, but the thing is, some of that 51 also said Larry, and some of them said Curly, so we need to account for all that. All right? So what I like to do is wherever possible, account for the overlap first. All right? So I would jump right on down to the case where all three of them are accounted for. All right, so I would start with this one here. 24 admire all three. So that I know is going right in this little wedge there. All right, so that's where I would start. Then from there, I would look at other forms of overlap. You know, whatever jumps off the screen at me. But I see here 34 admire Mo and Larry, so that's the overlap between M and L. So 34 would go here. And get another color involved. 32, Larry and Curly, that's the overlap between L and C. Get a fresh new color here. All right, so then we have 36 that admire Mo and Curly, so that's the intersection or the overlap between M and C. So that's 36 right here. All right. They say that one individual admires none of the Three Stooges. All right. So you could put one out here because in the null space outside of the circles, those are the individuals who don't admire any of them. All right. So in that overlap, now this is the tricky part. It's very easy to lose sight of these things. This 34 corresponds to this whole shebang. I don't know a better way of shading that. And also, I'm kind of tucked into a corner here. It's like I'm not in love with this setup, but I'll figure it out. I just got disconnected and reconnected. All right. Some things are working out. All right, let me fix this up a little bit, make it look a little nicer. I'm just going to thicken my marker because I don't like the way that looks. So this little wedge, or big wedge here, I guess. I mean, wedge-sized wedge. That is what the 34 is referencing. But if you look closely, you realize 24 is in there also. So if the 34 represents that entire wedge, we'd have to subtract the 24 from the 34 in order to get the true value inside this. Let me get I'll go some form of green here. This wedge here. In order to get this, I have to take the 24 away from the 34. Just bring it in a little bit. So there's only really 10 true values in that region. So knock off the 24. There's only 10 in here. All right, and that's the same idea for the 36, because this 36, again, I wish there was an easier way to toggle back and forth between the colors, because that gets distracting. So this whole kind of ellipsoid looking figure, that's where the 36 is coming from. So from that 36, I want to knock off 24. And that's going to leave me with 10. All right. Sorry, 10 was before. I just stared at 12 is what I meant to say. All right, so there'd be 12 individuals left over for this little region. Then the 32, again, that applies to the entire wedge. So all of this all right, so from there I knock off 24 and I'm left with 8 individuals. All right, so we have 10, 12, and 8 as the relevant values. Now you don't have to show the computations, but it's easier to kind of keep track of it if you do. Yeah.
Why are we subtracting the middle number from each wedge? Because on the list of surveys, it says, so for example, it says the shared space between Mo and Larry is 34 on the list of surveys, and that looks like the space that. Do you know what I mean? Wouldn't you write 34 in that wedge because that's what it says on the survey?
Yeah, but the thing is, we know that these individuals like, let's say, Mo and Larry, but we don't know what else they like. So they're only, in a manner of speaking, it's sort of like a trick question, in the sense that.
So if it was 34, we'd have to say 34 like Mo and Larry, but not.
Yeah.
Okay.
Yeah. And honestly, that's one of the reasons why when we go over when we do something like this, I do it in a form of like an activity rather than a test, because I'd really have to spell it out on a test and say, Mo and Larry, but not Curly. Mo and Curly, but not Larry, and really it defeats the purpose. But it is a lot, right? And also there is a school of thought where if the question framed it this way, and I admit I got this from a textbook somewhere. If they framed it a certain way, they could say only, so 51 only admire Mo, 49 only admire Larry, and so on. In which case, that those are the numbers that go right in the slot, no questions asked. All right, but because they left that gray area here, that made it a little bit more complicated. All right. So then, when we look at the Mo category, so going back to that, so that's this one here. We have 51 individuals that admire Mo, but maybe they also admire Larry. Maybe they also admire Curly. Maybe they admire one but not the other. Maybe they admire all three. So from the 51 that admire Mo, we're going to subtract off anything else that's in the Mo sphere of influence. So I got to knock off a 10, a 24, and a 12. All right. And that it's along the same lines where it's like, okay, well, how do I know that that's the case? Again, it's the great, and I think it's one of the reasons why probability is so difficult. Not because the concepts are hard, but because I don't think there are many people out there that could word the perfect question when it comes to probability. It's usually like, all right, I'm going to write down something that I think makes sense and ask people about it, and they're like, oh, but what about this? What about that? And you're like, oh, I didn't think of any of that. All right, so yeah, we'll get to more realistic cases as we go. And in fact, if you're the one that's in charge of collecting the data, then it really becomes easy, right? Because if you're going around asking people what their favorite food is, who their favorite superhero is, and what their favorite sports team is, then you're cataloging all that information as you go. Some people are going to have commonalities in some areas but not others, and it's easy to keep track. But when you don't know how many people are surveyed, that's when it gets a little dicey. So 51 minus 10 is 41, minus 24 would be, 17? So there's really only, I believe, 5. Double check that. Let's see, 17, 4, yeah, so that works. So there's actually only 5 that just like Mo. They're exclusively Mo fans. Every one of the remainder of that 51 person group liked some combination of Mo along with other people. All right, so we do the same thing with Larry. All right, so Larry has 49 admirers. So we knock off anything that's in the Larry sphere of influence, minus 10, minus 24, minus 8. So 49 minus 10 is 39. Then we're looking at 15 when we subtract off the 24. Then we subtract off 8 from the 15 and we get 7. Calculators are totally fine and encouraged. The only reason I'm not pulling one up here is because I think it messes with the zoom. It's going to be harder for you to see the work if I have a calculator up there. So correct me if I'm wrong on any of the in my head on the fly computations, because I'm good, but I'm not that good. All right, so we have 60 individuals in the Curly category. All right, so knock off anyone else that's in the sphere of influence for Curly, but not exclusively Curly. So I'll take off the 24, the 12, and the 8. All right, so that's a subtraction of 44 from 60. All right, so that's going to be 16. And whoever created this question, they must have been Curly fans, because it looks like they kind of tailored everything so that it would be like Curly centric. Right? So it's possible, but they could have just made up some numbers and hoped for the best. Right? But that's in its messiest form what the Venn diagram is going to look like. Right? As opposed to just kind of trimming out the fat and just putting M with a 5, L with a 7, C with a 16, and then counting all the overlap and just throwing it in there. Right? But the recipe to success here is work inside out. Right? The most overlap to the least overlap. Right? And it tends to get a little better from there. And then they ask how many people were surveyed. Well, now we know each category. You know, we got the Moes and the Larrys, but not the Curlys. The Curlys and the Larrys, but not the Moes. All three, none of, you know. So we can answer every question that follows. How many people were surveyed would just be the sum of all the values in each circle. So I'll just write them all out. 5 plus 10 plus 7 plus 12, 8, and 16. All right, so 15, 22, 34, 42, 58, I think. So 58 individuals were surveyed. Just do a quick double check on that. I'll add it the other way. 24, 36, 43, 53, 58. All right. Yeah.
What about the 24 in the middle?
The 24 in the middle, the one I completely whiffed. Yeah, good call. Thank you.
So you gotta remember the one outside.
And the one outside. All right. All right. So 83, 58, 68, 58, 78, 82, 80. I believe 83. Sorry. I try to keep it interesting, but you know, sometimes it's Venn diagram, so maybe a loud yawn is required to get the point across. I try my best though. I'll make it more fun, I promise. You know, it's just that you got to get through the skills first before you can get to the really interesting stuff, you know. And I don't want to throw a video at you and make you watch it and say, learn all this stuff so we could just do the fun stuff in class. So, yeah, it's a little dry. I'm the only one talking. It's like there's dead air when I'm not saying anything. And so, yeah, it could be a little tedious. So I'll try to do better. All right, so how many admire Curly but not Larry nor Moe? All right, so that's basically saying you're living in the Curly category with no overlap, which sounds weird when you say it that way, but that's the 16 individuals that are in the Curly space. How many admire Larry or Curly? All right, Larry or Curly would be anyone in the sphere of influence between Larry and Curly. All right, so it could be Larry all by himself, Curly all by himself, or anybody in the middle between Larry or Curly. So this is, again, it goes in the category of it could get a little mind bendy, but I'm basically saying I'm gonna shade it in, but then I'm gonna unshade it. I just need to prove the point. So here's Larry. Here's Curly. We're accounting for anybody who falls in either of these circles, including the people who fall in the Moe circle, because they never said anything about Moe. All right. So we account for anybody in either of these circles. So we got the 7, the 10, the 24, the 12, the 8, and the 16. But if you think about it and just look at what we didn't shade in, that's anybody who's exclusively Moe or didn't like any of them. Like, I don't like any of the Three Stooges, right? So instead of saying, let's add up these values, I can take the 83 here. That's not a highlighter. the 83 here and knock off the 5 and the 1 that don't fall in that category. Or I could just add them up. There's multiple ways to go after it. All right? Sometimes do it both ways, use one to check the other. All right, so 24, 36, 40, 60, 77. How many admire exactly one of the Three Stooges? All right, so now we got to infer what it's asking us. Exactly one? Well, which one? Well, any one. I'm just going to get this out of here. So that could be they only like Mo, or only Larry, or only Curly. All right, so those are the ones in the circles but without the overlaps. So I got the Mo, only Mo, that would be this group here, these 5. Only Larry would be these 7, and only Curly would be these 16. So plus 5 plus 7 plus 16. So that's going to be 28 individuals. The next one is just the previous one, but to a higher degree of difficulty, because now it's saying how many admire exactly 2 of the Three Stooges. So that could be only likes Mo and Larry, only likes Larry Curly, only likes Mo and Curly. All right. So I'm going to write all that down. Only, I'll use M and L. Only L and C. Only M and C. All right. So going back before, where we had to assume that when somebody liked Mo and Larry, yeah, they could also like Curly, they just didn't say it. Right? Or maybe they like Mo and Larry and, Thomas the Train. Some other category that we haven't accounted for. But what this is saying is that we just want the overlap, but not between 2 circles, not including the third circle. All right. So between Mo and Larry, that's the 10 individuals. The Larry and Curly would be the 8 individuals, and the Mo and Curly would be the 12 individuals. So add those up, and you get a total of 20. All right. But this question is like the gray area of all gray area questions, okay? Because interpreting what they're asking for is the biggest challenge. There's so much to interpret. Oh, thank you. That's why I need a TA. There's somebody that, like, while I say things, to actually do the writing for me. Because it's like walking and chewing gum at the same time. It's always tricky for someone like me. Just get rid of this. Yeah, but that was a beast. Look at that. Right? Like I said before, don't get too down on it. It's it's not something necessarily that you're interested in. So it's I'm not talking about the concept. I'm talking about Mo, Larry, and Curly. So you throw in something that you're more interested in. Now you have something that you can kind of sink your teeth into. And when you collect your own data, it's going to be even better. Right? So I kind of look at it like, if I'm surveying 3 different locations to open a business and I'm relying on foot traffic, I might want to know certain things like how many bus stops are in a certain radius around each location. Right? Are there residential apartments? Right? Or maybe office buildings where people come out during lunch. Maybe it's a restaurant, maybe it's a deli service, something like that. Like, these are the different variables and how they interact that might determine why I would choose one location over another. So one has high foot traffic due to residential apartments, but it doesn't have any bus stops. All right. One has bus stops and office buildings, but not residential. Right. And so you can kind of piece it all together and decide what it is that you need for your business, and use this knowledge. I'm not saying you're going to draw a Venn diagram for it. Right. Although if you do, like 5 years from now, if you find yourself drawing a Venn diagram and it helped you in real life, please send me an email and tell me, because then it makes me teaching this class a whole lot easier when I can say that somebody went out and actually used this. I can tell you that you could use it for things like games of chance. We'll talk about roulette later in the course. Other casino games, and you'll see, because you could make multiple wagers in a game of chance. Maybe you're betting on red, but you're also betting on the even numbers, or maybe betting red, betting on even numbers, and then also betting on the number 7. And so you look at it and say, well, that's easy. I don't need a diagram for that. You don't need a diagram to figure out how you would win. You might need a diagram to figure out what you would win if you won. All right? Because maybe you win on red, but you lose on the bet on 7, and therefore, if you bet on odd, for example, you may have lost that bet too. Because maybe the number 6 came up. So the payout odds work into that. It gets really complicated. You might find yourself making a spreadsheet, making tables, but it's all going to be rooted in this concept. So there is value to it. It's just I wouldn't even believe me at this point, right? With Mo, Larry, and Curly, but we'll get there. All right. We left off also with truth tables, because in order to determine which overlaps are relevant, you need to know the truth, right? Because it really just boils down to always true, sometimes true, never true. So when you think about any event, person likes Mo, person likes Larry, person likes Curly, it is true that they like Mo, but not true that they like Larry, but it's true that they like Curly. It's really feeding into the same thing. All right? So we're allowing for multiple truth values to work their way into a situation. All right? Some terminology. If a sentence is always true, we say that it's valid. Another word for that is a tautology. Right? If a sentence is always false, we say that that's unsatisfiable. We also could say contradiction. Basically, the tautology contradiction is more the math terminology. The valid unsatisfiable is really the more everyday way of saying it. And the last possibility is it could be a mix of true and false, which means it's satisfiable, but only under certain circumstances. All right? That's the gray area. And again, the notation is going to be pretty heavy, but we'll get through it. So what we want to be able to do is determine if a situation will always lead to a true outcome, always lead to a false, or under what circumstances will it lead to a true outcome. All right. Generally, a false, we like to know that too, but we focus on true, because if something is not true, then obviously it's going to be false. All right. So just a quick review. The and. So if I have P and Q, all right, that's the conjunction. Conjunction. And it's only true if both parts are true. This is all written in the notes previously, but it's good to keep sort of reinforcing. Only true if both parts are true. And then, that's not a P. P or Q, disjunction, only false if both parts are false. Right? Only false if both parts are false. The weird one is the conditional. P then Q. That's a specific occurrence. Right? If you have P then Q, it's only false if it's the first part, in the case of the first part is true and the second part is false. Right, that's the only instance in which it'll be false. Those are called counterexamples. They're the statement that proves the rule, or the exception that proves the rule. So if you know under what circumstance a conjunction is true, or disjunction, or conditional, or false, then every other instance has to be the opposite outcome. All right. Now we did a little bit with the truth tables last time, and we kept it simple. This is really the more valuable stuff. When I say a sentence is valid, unsatisfiable, or satisfiable, I'm really just looking at that last sentence there, right? And again, it's contextless, but you could throw some context. I mean, I could steal the context for the next question here, where they tell you what P and Q represent. All right, that's for a different problem, but you could apply anything you want. Any statement, just a quick declarative statement that could either be true or false. Right? I have taken out the trash, and I have finished cleaning the dishes. Then I have taken out the trash, or finished cleaning the dishes. Doesn't feel like much of a useful sentence there. But if we could determine whether it's true or false, then we're really getting an idea of a structure that leads to a true outcome, or false, or otherwise. So going down the list for P and Q, it's only true if both parts are true. So these are the both parts, right? The only instance in which it would be true is that one. Everything else will be false. Going back to the P's and Q's. Minding our P's and Q's, some might say. And if I'm looking at these and I'm using or applying the disjunction rule, it's only false if both parts are false, then I would say true, 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 false. All right. And so the last bit here, that last column, is really just telling us to ignore the first two and focus on these two and apply the conditional rule, all right, the sideways arrow rule, which says a sentence is only going to be false if the first part is true and the second part is false. All right? And that never happens. So this sentence is what we call valid because it's always true. All right? But it's a very simplistic sentence, I would say. Because I always start off my discussions of logic by talking about shoes and socks. I mentioned that last time. I am wearing shoes. I am wearing socks. We can easily determine the truth of that. Possibly, it might be a stinky proposition, but we could determine whether it's a true sentence or not. There's really no gray area. Am I wearing shoes? Am I wearing socks? Very easy. So a way that this could be read is with the P representing I am wearing shoes and the Q representing I am wearing socks. If I am wearing shoes and I am wearing socks, then I'm wearing shoes or wearing socks. It's like, well, yeah, it's going to be true. Because if I'm wearing them both, that's a true sentence, then it must be the case that I'm wearing one or the other or both. All right, so we got it covered. So it's like if I say I am wearing shoes and socks, and you turn around and say, "But are you wearing shoes?" Be like, I just answered the question. Like, what are you asking? You know. So again, a simplistic sentence because nobody speaks that way, right? But in the case of like writing up a contract, if somebody has really good sense of logic, they could spin you around and put you in a corner. You agree to something only because you don't know the logic, you don't know how to decode it. Right? So what we want to be able to do is take something like this, which is fairly complicated, and simplify it. Right? So what are you really saying? You know, that's really the key ingredient. Right? So that's what we're working towards. Right. The second one, give a little context here. I have taken out the trash is what we're letting P be equal to. I have finished cleaning the dishes. And then a third component here, which is the first time we're dealing with a third component for truth tables. I have watched 5 hours of TV. Right? So this sounds like, you know, a rule that one might have at home. So hey, the blurb there, assume a child is good. You could be good for a lot of different reasons, but under these circumstances, if that statement there, the P and Q or not R, holds true, and bad otherwise. It's really cut and dried, but you know that's what we're going to go with. And we would want to know under what conditions is a child good. All right. So you kind of look at it like, all right, so if the first two sound like chores, and the last one sounds like a reward, so I would think that something reasonable would be, okay, you got to do this. You got to take out the trash. You got to do all the dishes, and then you can watch TV. I don't think there's ever a circumstance where I told my kid, specifically, you can watch 5 hours of TV. That seems like a little much, but you know that's the blurb here, all right? So you may be wondering why there's so many more possible outcomes in the truth table. Right? We have a third variable that's going to add a third component. So if we look at this and say, all right, well, P can either be true or false. All right. Q could either be true and false, but it depends on what P was. All right. So it's possible that for P and Q, we could be looking at, you know, between the two, upwards of 4 possible outcomes. Because maybe it's the case that P is true and Q is true. P is true and Q is false. P is false and Q is true. Or P is false and Q is false. Right? That's actually where these values come from. You go across the line. True, 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 false, false, true, false, false. That's where all this stuff is. All right? But now we're incorporating a third variable, R. So an extra branch containing true and false. So the first branch, or the first pathway, true, true, true. Second one, well, it could be true, true, false, but I wrote true, false, true. Every possible ordering is accounted for. It's just sometimes when you do a tree diagram, it's in different order, but that's okay. All right, so every outcome for Q gets a true or false. And so we end up with this much bigger tree diagram containing 8 values rather than 4. I mean, for one variable, you have two possible outcomes. For 2 variables, you have 4. Then you go up to 8. If I threw in a fourth variable, you'd be up to 16, then 32, and then after that, you'd run out of room. I mean, you need a spreadsheet, all right? So the more variables you incorporate into a situation, the more complicated it gets. But I don't think you need a tree diagram to determine that, all right? So you think about it like, how do I get to work in the morning, right? If it was just a matter of one step, either turn left or turn right, a pretty simple process. But then I have to walk down the stairs without tripping and sliding down the stairs and getting bruised. Right? Then I got to get in a car and not hit the deer that's crossing the road. And I got to say, honestly, I almost got into 4 accidents today. One involved deer crossing the road. One involved a bunch of cars that were going around. So there was a bus coming in this direction, right? It was stopped, and all the car. It's two-lane road, one each way. Bus, cars behind it, impatient, coming around. The last one comes through. I go. The guy behind the bus doesn't see me, jumps to turn, and I almost plow into him. All right, so that's two. A similar one over in Elmsford. What is that? Sawmill River Road, southbound. Somebody's making a turn left. Truck. Car's stuck behind it. I'm in the right lane. I have the right of way. The car that was stuck behind the truck is like, well, I'm going now. And went. That was number 3. And number 4 was almost a head-on because 2 lanes going opposite directions. One person on their phone. Spoiler, wasn't me. That person swerved into my lane. All right, so all those different variables could have, or any of them could have kept me from getting here tonight in a very painful fashion. So fortunately, they were all false. Right? Did you get into an accident in that instance? No, false. True or false? You got into an accident there? False. The stretch of false outcomes is what allowed me to get here safely. All right? So that would be this set of occurrences. All right? So sometimes false is not a bad thing. All right? True would have been devastating. I mean, if I got in 4 accidents in a single day, that would be awful. I don't even want to get into, because karma's a thing. And also, like, I believe that if you have a string of good luck, this is the old married with children rule of thinking. If you have a string of good luck, but then admit it, hey, I'm on a lucky streak, you will immediately be met with a string of bad luck equal to the size of the good luck. So if you win Powerball and then say, I'm the luckiest guy on earth, you're going to get struck by lightning. I mean, it's just a guarantee. All right. So, words of wisdom. If you win the Powerball, be humble. Don't say anything to anyone. Besides, you don't want to get robbed. You're just better off. All right. So, I've taken out the trash. I've finished cleaning the dishes. I watched 5 hours of TV. All right. So, we're just going to go by the rules of logic here. And we're not going to try to wrestle with, all right, the first part's true, the second part's true, the third part's true. What does that mean for the whole thing? All right. Now, what this sentence would read as is, I've taken out the trash. And then it's the whole sentence here, even though the arrow is making it seem like I'm pointing to just the R. I've taken out the trash, and I have either cleaned the dishes, finished cleaning the dishes, however you want to say it. I'm just going to say clean the dishes, otherwise this is going to become an essay. Or watched 5 hours of TV. I'm just going to say watch TV. All right. Not. Thank you. Or have not watched TV. All right. So to parse through the circumstances in which this sentence would be true, not the easiest thing in the world. All right. So what we do is we break it down into smaller pieces. We tackle order of operations, applies to math computation, it applies to logic, it applies to Venn diagrams. If you have an expression that has parentheses in it, you always tackle that part of it first. All right. So we're going to look at Q or not R. All right. That's where this column is coming from. Now, you may want to make like a skinny new column there because we don't have a column of just not R. We have a column of R, Now, if you want to just talk it out to yourself, you could say, all right, let me look at these two here. True or the opposite of this. True or false. Okay, that would be true. You know, you could do it that way. But if you're a more visual style of learner, then what you could do is tuck in a skinny column here and just throw it in before the R and call that not R. All right? And all not R is the opposite of anything that you have in your R column. Right? So that should be easy enough. So this is true, so it becomes false. False, false, false. This is false, it'll become true. So true, 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 true. So now I have two columns adjacent to one another, and that's the reason why I put it in front of the R column and not after, so that you could have them right next to each other. You're not always going to be able to do that, but when you can, you should. And some people just will draw an entirely new table and do it that way. All right? But I'm looking at Q or not R. Again, the rule for OR is it's only false if both parts are false. All right? So that's not the case here. So this would be true. It is the case here, so that would be false. True. We get false or false, so that's going to be false. But every other instance involves true in some capacity. So true, 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 true. All right. So then what we want to do is apply a conjunction. So again, we have this conjunction here. Let me use a thinner highlighter. That's comparing P and what we just came up with. All right. So that would be these two columns. Oops. This one combined with this one. So the result of the first, I'll call it computation. In a manner of speaking, it kind of is. But the result of the first one applied again to the P column. All right. And again, the only time a conjunction is true is if both parts are true. All right. So looking at my orange columns, I'm looking for any instance in which they're both true. So that happens here. Not here. So that would be false. Same deal for the next two outcomes. So false, false. All right. A couple of trues. So we're good there. Another couple of trues. Everything else is going to be false. All right. So the instances that we care about, I'm going to go with the reddish hue at this point. The instances that we care about would be this, this, and this. Because we want to know, because they did ask us, under what conditions is a child good? So that would mean that the truth value of behavior being good would be true. All right. So we go back to our original P, Q, and R and only take the relevant ones. P, Q, and R. The ones that worked, the ones that gave us a true result were true, true, true. True, false, true. Lost my place here. Oh, that one's incorrect. Hold on. True, true. I was looking at the wrong column. True, true, false. Because I'm looking at this column, and this column. All right. The ones that correspond with what I highlighted in red. All right. So that's going to be true, true, false. And then the last possibility would be true, false, false. All right, because you think about it, and again, I'll get into what this means in terms of the actual problem, but you're rewarded for doing what you're told, right? So I'll give a simple example. If you wash the dishes, then you get a reward, right? It's a very simple case. It's like it seems pretty cut and dried, but that doesn't mean you're a bad person if you didn't do the dishes and didn't get a reward. You know, like, I was supposed to do the dishes. I didn't, so I didn't get the reward. That's fine. And it is possible like if you think about from the perspective of a child, your parent would still give you a reward anyway. It's when you go looking for something that you're not entitled to. So it's the case of you got a 70 average and you go barging into the professor's office saying, "How dare you not give me an A?" Like, why would I? So that's not the grade that would meet the requirements of getting an A, right? So you're not necessarily violating the rules of this if you didn't get the outcome you wanted. You just need to, adhere to the structure of the rules, I guess, right? But in terms of what this is saying again, because our whole sentence here was, I've taken out the trash, and I've either cleaned the dishes or not watched TV, all right? So if I say the whole thing is true, and each part is true, then I'm saying I did take out the trash, and the crux of the whole thing would be whether I did the dishes or I was unable to watch the TV. All right? Because if I didn't do the dishes, then I shouldn't be able to watch TV. All right? So these are the different instances that lead to a true outcome. So these are the instances that satisfy this hypothesis. So we call this satisfiable given these conditions. Terms of agreements, things like that. You don't have to meet all the terms and conditions for, let's say, optimum TV, internet service, whatever. But if you don't meet the conditions, you don't get the service, right? So there's nothing wrong either way. You meet the terms and you get the product. If you don't meet the terms, you don't get the product, and nobody's upset because that's what should have happened, right? So this accounts for the different ways that you might be able to satisfy the terms and conditions and still get the outcome. All right? So not every part has to be true is the moral there. All right? But, like even this sentence here, I've taken out the trash and I've either cleaned the dishes or not watched TV, even that's a little more complicated than we would want it to be. All right? So what we want to learn about is ways that are equivalent, or language that's equivalent, but not as complicated. All right? So that's probably a good thing. Like we want to make things easier to understand, not more complicated. And it's pretty rare in a math class. They start off the course with stuff that's really complicated, and it gets easier to understand as time goes on, rather than starting the course off with the easiest stuff, and by week 10 you're like, I don't understand anything that's going on anymore. So I like to do it the other way. Make you not understand anything early, and then teach you ways to understand by simplification. All right? So it kind of sounds like I'm attempting to make a joke, but it's actually the reality of things. That's the nature of logic. All right? So logically equivalent statements is where it's at. Because if we can take something that's fairly complicated and clean it up, then we're going to be in a pretty good spot. Conditionals are the most complicated thing in propositional logic, right? Just because of the if-then aspect of it. Because generally it's not, like I said before, if you get a 90 or above, then you get an A. It's usually something like, if you do this, that, and that, then you can get this, that, or that. And you're like, oh, okay, so under what circumstances am I going to get any kind of reward out of this? I don't know. So you simplify things. Very rarely are people going to be sitting down making truth tables, but worst case scenario, you do that. Okay? But we have something called the biconditional that'll allow us to make a determination of truth. Little typo. There should be a double-sided arrow. And then by extension, so should this. All right. What this is saying, and we touched on this with the Venn diagrams, but this is saying that P then Q means the same thing as not P or Q. All right. So that's what this is saying. Means the same thing as. And it's more of a lay term way of saying it, but it's talking about just being equivalent logically.
Yeah, I was just gonna say those two arrows basically just mean equals.
Yeah. Yeah, just think of it as the logic equal sign. All right. So, I mean, you can make a sentence out of it. I'll go with the shoes and socks. I know it's simplistic, but I don't want to make things too complicated too quickly, even though that goes against what I just said not like 2 minutes ago. So if I am wearing shoes, then I am wearing socks. I mean, you can make a case that this sentence actually makes sense. I mean, it wouldn't always be true, but especially this time of year, if somebody came in wearing shoes, you're probably going to assume that they're also wearing socks. All right, summertime, different story. It's warmer out. Right? Some people are just anti-sock. I respect that. This means the same thing as I am not wearing shoes or socks. I mean, you could also be a little bit more verbose with it and say I'm not wearing shoes or I am not wearing socks, but you could also kind of condense it a little bit. All right. If I am wearing shoes, then I am wearing socks. It means the same thing as I am not wearing shoes or socks. All right, but we got to be careful because there's the either or that we think about when we use the word or in real life. Makes it seem like a choice. All right. In this case, we're allowing for both parts to be true at the same time or either part to be true. All right. And so logically, we can determine the truth value using truth tables, but it's the kind of thing that it doesn't really feel that good in terms of the connection between the two. But I can tell you that when we get to probability, evaluating probabilities involving if-thens way more complicated than just simple ors. All right. So if we can transition from an if-then to an or, we will make our lives easier. All right. So true, true. I'll do it down the line. True, true, false, false. True, false, true, false. All right. So ultimately, we want to get to this. If I just gave you this sentence and told you to evaluate the truth of it, you might not include all of these columns. I just did it to try to make it a little bit easier to kind of see the relationship. All right. So one of the ingredients is that we need a not P, so I figured make a column for not P. All right. So we're just going to take all the P values and negate them. So that becomes false, false, true, true. All right. Now, addition and multiplication, just going back to algebra, beginning algebra, even like middle school, they're commutative operations, which means you could do them in either order. So when I see something like 2 plus 3, I could treat that like 3 plus 2. Right? It would amount to the same thing. But I could do the same thing with an or an and. So I could look at this as the same as Q or not P. That it doesn't seem like a big deal, but it allows me to look at these two columns in helping me determine the fourth column. Right? So putting these two columns together allows me to come up with that fourth column using the rules of OR. Rules of OR says the only time we're going to get a false is if both parts are false. All right? So that doesn't happen here, so true. It does happen here, so false. The other parts are true. I also look at it like if there's a true in there anywhere for an OR, the whole thing's true. All right? And it's kind of like the same thing with and. If there's a false in there anywhere, it's false. You look at little different mnemonics to help you remember this stuff. All right. But then P then Q, we're going right back to the first two columns. It's the foundation of building a logical argument. Right? And you do that in all sorts of other areas, like research papers and things like that. But you never really think about the logic of it. You just think about, okay, hey, do me a favor, read this and tell me if it makes sense. And that's as far as you really get. But if you want something to be logically sound, you want to consider all the different ways each part can be true or false. All right. So for this one, oops, that's not the color that I want. I'm just looking at the rules of if-then and how they apply to the values that I have. The only time an if-then is false is if it's true, then false. All right. So I use that little reference there as a little reminder. If it's true, then false, it's false. Otherwise, it's going to be true. All right. So true, false, true, true. Now this last bit is just asking us to determine whether there's equivalence. All right. So if I look at these two columns. Let me just get my words and my writing to catch up to one another. These two columns, that's going to help me evaluate this, which seemed overwhelming before, but since we chunked it into smaller pieces, it got a little easier. All right. That equal sign is really, that biconditional is really an equal sign. So you're just asking yourself, are the truth values the same? All right. These two are the same. These two are the same, same, and same. All right, so the conditions that make one part of it true are the same as the conditions that would make the other part true, which means that they're equivalent logically. So true down the line, again, we call that a tautology or valid. Valid is an easier word to say, so that's the one I go with. All right, valid, and when I say valid, I mean valid in every possible situation. All right. Since there's only 4 possible situations, it's really not earth-shattering, but it's pretty valuable. Instead of boring you to tears, I don't think we're at tears yet, but I want to try to steer away from that. I'm just going to give you the rules for converse, inverse, and contrapositive, and not bother with proving them, right? Because this was a proof. And this is actually the most valuable one for us in terms of evaluating probabilities. But the other ones are pretty useful too, but I think it would be the entirety of the remainder of the class going through those. So I'm just going to give you the rules. A converse is when you switch the premise with the conclusion. All right. Inverse is when you negate the premise and the conclusion. And the contrapositive is when you do both. You switch them and you negate them. All right. So the first one and the second one are not equivalent to the P then Q. All right. So it is not the case that we have a valid argument if we were to say that this was the same as this. All right. And, you know, the simple example is if you get a 90 or above, then you get an A. Just flip the premise or the conclusion there. If you got an A, then you got a 90 or above. Not necessarily true, right? If one argument is true, the other one does not necessarily have to be true. It can also be true, but it's not always going to be true, right? The only one that's always going to be true would be the contrapositive. So as a byproduct of all this, oops, that's not what I wanted. We get P then Q is equivalent logically to not Q then P, then not P. All right, this is the only one that's actually true. So the contrapositive, if we were to go through all the truth tables, you see that that would be the one that worked itself out to be the, we'll call it the winner. That's the one that's logically equivalent. All right. So we get a couple of rules out of this. One is the one that we proved, and this rule, but it helps to simplify things. Not so much going this way to this way, but going the other way, because negations are kind of confusing. All right. So it's like, I ain't gonna cut class today. Like, well, the cutting class would be a negative. So I'm not gonna not go to class. Okay, so I'm going to class. All right, why don't you just say that? You know? So if we can get instances that have conditionals involving negations in it into another form, a simpler form, then it's going to be easier to interpret. All right? And so we get to skip all this stuff. If that's the moral of the story, then that's what I'm willing to accept. The next page is laws of logic. There's a lot there, and it's not the kind of thing that I would want to just kind of throw at you and say, oh, let's go through them one at a time. And it's like, oh, we'll be here to next week. All right, but what I'm going to ask you to do is look this over for next class, and we'll talk about how we could make use of this information. Some of them are a little bit more common sense, and some of them have typos in it, apparently. Right off the bat, the one I notice is my law of double negations. That should be not. So that's not good, but make the adjustment on yours. You can't have a double negation if there is no double negation. All right, so with that, I'm going to say let's take a break, and then we'll come back, and I have a little activity for you involving Venn diagrams. All right, and that's really all we're going to do for the remainder of the class. So it's break time, Venn diagrams, and then that'll be it.